Okay, okay. So, I am Banik. I am from IIT Madras. I will give a talk on nonlinear spinel effect in quantum materials, and I am doing project with Sir Professor Ranjit Kumar Nanda. So, I'll go through first. This is my content of today's presentation. So, I'll go through first what is the classical Hall effect. So, we all know that. When you put a electric field perpendicular with a magnetic field in planely in a material, we will get a out of plane Hall current, which is well known, our classical Hall effect. And then I'll go through that symmetries in the electronic band and the idea of the Berry phase. From the left figure, from the first one of the left figure, we can see that at a constant k in momentum space, will for spin up and spin down electron will get the same energy, and for different k with for k plus and k minus for the same spin, like for suppose spin up or spin down, will get the same energy. So we can say that from the first figure that it will the system is conserving the time reversal and inversion symmetry. So
Rajdeep,
we can, yeah, yeah,
Rajdeep,
yeah.
sorry to interrupt you. Can you please go to your presentation mode? The slide is not on full screen.
Slide is not.
Full screen. So can you just go to the presentation mode so that it's in full screen?
Uh,
You can you find some for a slideshow? So you have a slideshow option somewhere.
can you see now?
Yeah, this is perfect. Yeah. Sorry. Yeah. Continue, please.
So should I start from starting, or can I continue after that?
No, just continue from where you were.
Okay. So if the time reversal and inversion symmetry is concept there, we can say that the Kramer's degeneracy is there, and you can see the condition for the Kramer's degeneracy. So I'll now introduce what is the Berry phase. So if suppose if a system is adiabatically going through a closed loop, then the wave function of the system will gain a geometric phase which is not dependent on the time, rather it is dependent on the path the system will be going through. So this geometric phase is considered as the Berry phase, and we will get from that the Berry curvature definition, which is expressed here willly. So the Berry curvature is defined as like it is analogous to the magnetic field in real space, but it is defined in the momentum space or Berry curvature. So now, if suppose I have a system which has a suppose some ferromagnetic materials which has spontaneous magnetization, and this because of the spontaneous magnetization, a time reversal symmetry will be broken in the system. So because of that, if you integrate throughout the Brillouin zone, I will get a non-zero Berry curvature. So as I told you guys that the Berry curvature is like the magnetic field in momentum space. So because of that, we'll get a deflection of the electrons and we'll get a Hall current. So in my velocity expression, the first one is from the band velocity, and the second one is called the anomalous velocity, which is coming from the non-zero Berry curvature. So if my time reversal symmetry is not present, then I'll get a charge current. But if my time reversal symmetry is present in the system, and although if I want to get the current, so I have to break the inversion symmetry, and for that I will get a non-linear Hall effect. So what is non-linear Hall effect? In linear region, the current is varying with the first order of electric field, but in non-linear region, the current is varying with second with quadratic power of the electric field. So this is called, that's why called it is called the second order of current generation. So here I introduced that sigma mu nu, which is the conductivity term, linear conductivity term. The first term is coming from the band velocity, and the second term is coming because of the contribution of non-zero Berry curvature dipole, non-zero Berry curvature. Sorry. So here I will introduce the expression of Rashba SOC. So what is Rashba SOC? When a electron is moving through a lattice potential, because of the varying electric field, it will see a time varying electric field. Because of the varying potential, it will see a time varying electric field, and in its rest frame, it is feeling like a magnetic field. So electron spin will interact with this magnetic field, and spin up and spin down in electron will deflect to different direction. So because of that, our band will split into two bands, like here red and blue colors. You can see that the bands are splitting for spin up and spin down electrons. And So the we can see from the Rashba SOC term that as the electron is moving in the momentum space, because of its momentum is coupled with its spin orientation will change in a plane. So as the electron is moving, the spin orientation of the electron will also changing. So because of that, we'll get a Berry curvature, because the rate of change of the spin orientation will related to the Berry curvature. As fast the rate is increased, the Berry curvature will also increase. So after that, I'll my work is based on the tight binding model of a monoatomic square lattice with Rashba and Zeeman effect. So here I've considered that the xx1 term is coming from the Hoping term, and the two xx2 and xx3 is from the Rashba coupling term, which I have derived from the second quantization formulation, and I have considered the Hamiltonian. So here I have considered the, for numerical calculation, I considered the lattice constant as 1, and I have plotted the band structure. The first one is from when the Rashba and Zeeman terms are 0, and the second one I plot for Zeeman term equals to 0, but Rashba term a non-zero value, like 0 0.2. And because of that, I am getting a spin splitting, that like the spin up and spin down electrons are going to different bands, like that. And the third one is for when I put the Zeeman field, the band will get more dispersive. So because of that, I will get that band structure. Now I will represent the idea of spin Berry curvature and spin current operator. So my spin current operator is just like the anti-commutator of velocity. This is the velocity. This is the band velocity, which is the derivative of the Hamiltonian with respect to ky. And I have considered the out of plane Zeeman field with the with the plane where the Rashba field is um happening. So that's why I have taken the SZ component of the spin operator. So this is my spin current operator, and I have also expressed the expression of the spin Berry curvature. So I plotted the spin Berry curvature. The first one is you can see that the first one, the first one is for when Zeeman is 0 and Rashba is some 0.5 value. So you can see a peak at 20. But when I change the Rashba field from 0.5 to 0.9, you can see that the peak is going towards higher value like 60. You can see that. So as I increase the Rashba field, the with considering zero Zeeman field, because of the rate of change of spin orientation, the Berry curvature will become increased. And the second to one, when I have considered that the non-zero Zeeman field. So when I have considered a non-zero Zeeman field and I also increase the Rashba field, I am getting a higher peak at a higher Rashba value. I am getting a higher peak because when I increase the Rashba field, the asymmetry in the Berry curvature expression, or you can see from the plot that the asymmetry in the Berry curvature is become more prominent. So Berry curvature, so because of that, the gradient of Berry curvature, I will later I will express another uh, thing which is called the Berry curvature dipole, which is the fast moment of the Berry curvature. That when the asymmetry in the Berry curvature will become more, then the Berry curvature dipole term will increase. So here I have plotted. So there is a typo here. This sigma alpha beta gamma. This is the another typo. This is not orbital. This is for spin, and this is a linear spin Hall conductivity, and which is proportional to the summation over Berry curvature. And this Berry curvature contribution is coming from this should be a summation of occupied state. This is a typo here. So this is a summation over occupied states that. As I increase the Rashba field, the Fermi level will also changes, as because the band will get more dispersive. So the Fermi level will also changes, and because of that, the contribution of the Berry curvature from the k points below the Fermi level will also changes. So as I am plotting that the Rashba, the spin Berry curvature with the function of Rashba field, Rashba strength, I am getting a increment of the spin Berry curvature for zero Zeeman field, and it should be happen. And here I have plotted the spin Berry curvature dipole moment, spin Berry curvature dipole. So with varying Rashba field, when I have taken a zero Zeeman field, so I am getting here that the spin Berry curvature dipole also getting increased because the Rashba, because of this Rashba SOC, as I increase the Rashba SOC, the gradient of the Berry curvature in the entire building zone will get increased. So because of that, I'll get a more variation of the Berry curvature. So because of that, the fast moment of the Berry curvature will also get increased. So because of that, I'll get a increment of the spin Berry curvature dipole. So so
Zero, you
so
have 2 minutes left for your presentation.
hello,
You have 2 minutes left for your presentation.
huh?
Please go ahead. Please go ahead with your talk.
Okay. So now I had plotted only for Zeeman zero field, and now my future work is based on that how the spin Berry curvature and speed Berry curvature dipole will increase with Rashba when I have considered the non-zero Zeeman field. So this all.
Thank you. Thank you so much for your talk. Now we'll ask the judges if they have any questions. Yes, sir.
Hello, Rajdeep, can you hear me?
Yeah. Hello.
Hi, this is Rashish. You talked about two symmetries, one is time reversal symmetry and there is
Hello. I can't hear.
so I'm going. Hello, now I'm audible to you.
Yeah.
So you have mentioned about two symmetries. One is time reversal symmetry and the other is inversion symmetry.
Yeah.
And breaking of one of them, you were saying that it is the system is coming from the ferromagnetic phase to some other phase, right? That's what you said at the very first slide, right? Isn't it?
Yeah. For in ferromagnetic system, because of its domain, so there is
Yeah,
a spontaneous magnetization. So this
yeah,
spontaneous
right.
magnetization will break the time reversal symmetry.
Yeah, but then when there is this going from one domain to another domain, there is a
Yeah.
domain wall will be formed, and the decay of domain wall will inject some energy into the system,
Okay.
and will that change or modify the Berry curvature or Berry phase? Or are you aware of that, or I mean, does it make sense to you, or does it question make sense?
I actually I am
Didn't get
actually exploring that, but I don't know the answer actually.
you.
I,
Okay, thank you.
Thank you for your
thank you.
question, sir. Do any of the other judges have any questions? Anyone from the audience with any questions? Okay, we don't have any questions. Thank you, sir, for your presentation.
Thank you.